This video solves an Atwood's machine problem. In this Atwood's machine, the pulley at the top has a string around it, and the pulley is massless. The pulley has no friction, so it's not going to enter into our calculations. This particular problem, there's a 510 gram mass on the right side at the end of the string, and 220 grams on the left side at the end of the string. The distance above the floor is labeled for both of those objects, and we're going to do some calculations here on the dynamics and motion of this system. So let's get started with that. We want to calculate four things. I want to calculate the acceleration of the 510 gram mass. There is an imbalance in the masses, so the system will be accelerating. The acceleration of the 220 gram mass. Want to know the tension in the string, and I want to know the time for the 510 gram mass to hit the floor. The 510 grams, its weight is going to dominate the forces in this calculation. So the 510 grams is going to move towards the floor. Well, the acceleration of the 510 gram mass, we're going to consider the whole system here. So both the 510 gram and the 220 gram object, they're going to be in our system, and we're going to use net force equals mass times acceleration. How do we get some forces involved here? Well, the 510 gram object has a weight to it, mg, so minus 5.003 newtons. I'm using minus because the force is downward, and in this problem I'm electing to use up as the positive direction. The 220 gram object has a weight of minus 2.158 newtons. The total mass of the system is, if we add these two grams together, we get 0.73 kilograms, doing a conversion. And the net force, I hope you would agree that the weight of the 510 gram object and the weight of the 220 gram object, these weights, these forces, do not enhance the acceleration. They don't work together. They're opposing each other. Now, in my drawing, they're in the same direction, but the pulley changes the direction of force. So these two weights end up opposing each other, and to get the net force, we must subtract them. And we get a net force of minus 2.845 newtons. Calculating the acceleration then, net force divided by the total mass of the system. It is important to use the total mass of the system, not just the 510 gram mass. And we come up with minus 3.897 meters per second squared, rounding this to my typical three significant figures. We get minus 3.9 meters per second squared. That's the acceleration of the 510 gram object towards the floor, so it's a negative number. What about the acceleration of the 200 gram object? Well, just think about it. You don't have to do a calculation. It's tied with a string to the 510 gram object. This string does not stretch. That's typical physics string, and thus it shares the motion. It shares the acceleration number with the 520 gram object. The only difference is the 220 gram object is going to be accelerating upward. The 510 gram object on the right goes down. The string pulls the 220 gram object up. So plus 3.9 meters per second squared. What about the tension in the string? This tension in the string. This is an internal force in the problem, so I did not have to use it in the net force calculation. Net force only deals with external forces. But now we're going to take one object at a time. And I'm going to first consider the 510 gram object, and our system is just going to be this object. We're going to ignore the 220 gram object for a minute. The system is only the 510 gram object and the forces that apply to it, attached to it. So tension, that's upward in my drawing, so that's a positive. And then The weight is a negative number, minus 5.003 newtons. That's the net force acting on the 510 gram object. Its mass in kilograms, so use standard units, is 0.51. Change the 510 grams to 0.51 kilograms. And previously we calculated its acceleration, minus 3.9. You should pause the video now, use your calculator, and verify the numbers here. I'm adding 5.003 newtons to both sides, multiplying 0.51 times minus 3.9, and ending up with a tension of 3.01 newtons. 3.01 newtons. Is this reasonable? Well, I'd say it is reasonable because the tension upward of roughly 3 newtons is smaller than the weight downward of 5 newtons. This object will go down. The 510 gram object will move downward. The tension is not enough to keep it stable or move it upward. What about the 220 gram object? Now let's just focus in on 220 grams. The tension in the string acting upward on it here. Its weight acting downward, so that gives us our net force calculation. And then MA, and again I'm focusing just on one object, so I don't use the total system mass. I just use the 0.22 kilograms, and its acceleration is a positive. It's accelerating upward. Again, pause your video and pull out your calculator, and I get 3.02 newtons. I'm going to claim it is the same. It's 3.01 newtons. The only reason the number appears a little different is I've rounded here instead of keeping more digits in the calculation. So this is reasonable. We're getting the same value for the tension on both sides. There's only one tension number in this string, so that's reasonable to get the same number. What about the time for the 510 gram object to move down to the floor? Well, it's accelerating, so we're going to use a kinematic equation here. Let's write down what we know. We know our starting position is 1.3 meters up above the floor. We're going to end this motion when we hit the floor, so y will be 0 meters. We're going to start from rest. That was given initially in the problem. So the initial y velocity is 0. We do not know the final velocity. I'm not going to bother to calculate it either. But the final velocity when the object just touches the floor, that number is unknown. We know the acceleration. We do not know the time. That's what we're trying to calculate. So if you think about the 4 kinematic equations, the third kinematic equation, at least what I call the third one, is what we need. It does not have the final velocity symbol in it, and it has the t number that we want to calculate. So y minus y naught, the final y is 0, the initial y 1.3 meters. The initial velocity in the y direction is 0. We're starting from rest. And then 0.5, the acceleration, and t squared. Again, pause this, pull out your calculator, and I came up with t squared of 0.6666, a lot of sixes on my display. And taking a square root of both sides, I find that the time for the 510 gram object to move from rest down to the floor is 0.816 seconds. Is this reasonable? Well, suppose we cut the string and just let the 510 gram object do a free fall from 1.3 meters above the floor. When it's in free fall, its acceleration towards the floor is 9.81 meters, and I'm not bothering with the minus sign on both sides here. But the 1.3 meters the object moves down is 0.5, 9.81, and t squared. Again, it's this third kinematic equation. And I come up with 0.515 seconds, a smaller time. And this is reasonable when we're in the Atwood's machine configuration and there's a string attached to the 510 gram object, and over on the other side to 220 grams. The 510 grams is not in free fall. It is pulling this 220 gram object upward. Consequently, it takes more time to get down to the ground. So, reasonable result. So, there's the Atwood's machine problem. Net force is important. It is crucial that you decide what objects are in your system and write down your net force for your system. Don't use any internal forces. As we started off here, the tension of the string was an internal force. For more examples of physics problems and some short physics lectures, I have an annotated list that includes astronomy videos as well. gpclements.com. Everything's free here. You're not allowed to resell it, but you can use it all for free. You don't register, you don't give me your name, you don't give me your email address, etc. And my website does not have commands in it that would put cookies on your computer, so don't worry about that. Keep working physics problems and ask your instructor if you have questions.